Professor Manish Kumar. He got his PhD in environmental engineering from the University of Tokyo and is a fellow of the Royal Society of Chemistry. He has supervised 7 PhD theses, contributed more than 100 SCI journal articles, more than 40 book chapters, and edited 6 books. He has 20 years of experience in R&D, teaching, and also teaching. He's an editorial board member for Nature Partner Journals, Clean Water, Science of the Total Environment, ACS Journal of ES&T Engineering, and others. So today he's going to share the lesson that he learned from temporal monitoring of SARS-CoV-2 RNA in wastewater. Professor Kumar?
Yeah, thank you, Professor Yang. Li Ching has to stop the sharing, otherwise I cannot share.
Yeah, Li Ching, please stop sharing. Li Ching, are you there? Oh, okay.
Yeah. Okay.
Sorry, yes.
Yeah, no problem. Okay. You have stopped sharing the screen, right? Manish, can you try again?
Yeah.
Working now. Okay, yeah, working now.
Okay, sorry.
No problem.
So now, is it fine, Yong?
Yeah, it's fine now, working well.
Yeah. So thank you very much for inviting me and putting me along these so many stalwarts. Yeah, so we had a pre-conference seminar yesterday, and then it was told that please only explain or focus on your lesson learned or the challenges that was faced. So today I am going to talk about 9 challenges. I don't want to make it double digit, so that's why I kept it 9. But it's not that there is only 9 challenges. Let's start with that the sweep, that this term, surveillance of wastewater for early epidemic prediction. Of course, Professor Rose has already talked about like now we use term for wastewater-based epidemiology or sometimes just a wastewater surveillance. We came up with this terminology sweep that is, yeah, I mean, because what we can do with this surveillance is lot, but of course, the core of the technique is early prediction. So let me just give a little bit about this, what is sweep, because otherwise it will be a term unexplained. This is a framework. This is a framework which talks that, okay, whether you are targeting rural areas or urban areas, or you are doing, what is the level of the disease or spread, and so several aspects of this has been incorporated into this the framework. And using that framework, perhaps it is better, or it is we can go ahead. So this is the sweep concept. And not only that, using that, we can handle the outbreak, but we can also do prepare for the next outbreak. And of course, this paper is now online. So for more detail, of course, anybody can refer that. Let's start with the challenges list. I wrote E and C. E is experience and C is challenge. Of course, with experience, challenge can be overcome. And sometimes with experience, we know that what are the challenges. So the experience and challenge number 1, which genes to monitor? Of course, it may sound not so, the tricky, but yes, we have so many, so many kit to detect, and you know that this is a genome concentrate. This is a typical the RNA that will look like. Many of us measure N1, N2, and E gene. Some of us measure ORF gene, some of us E genes, and like that. So in my study, of course, because we are using TechPath, we measure 3. But none of the study is only relying on a single gene. So the multiple genes are being tracked. And of course, so that is a comparison among the various QRT-PCR kit. That, okay, the N gene seems to be much more common, but still I mean, the what genes needs to be monitored. That I feel personally is a challenge while matching my results with other. Then with that also, because we had a tech path kit, and we went with the spike gene. S gene is for a spike protein gene. Professor Rose has talked about that. N gene is one of the very, I mean, the most common that has been that are being taken care of, and ORF is some kind of a confirmatory gene for tech path also. So this was the first paper from India, and then it is that we have seen that there is no detection in treated water. So there was no detection in the treated water, and we just said that, okay, 8th May, we had a copy around 78, and which increased to the 800, 10 times increase has happened, and the COVID patient number has increased accordingly. So at least this technique can tell you that if the COVID patient number is increasing, number of gene copy found in the water is going to increase. That time the news was that whether it can help to detect the spread in the community or not. But gradually what we found is that at that time when we went for the sampling, I did the sample for several steps of the treatment plant. And here it was a very early one. You can see from the China septic tank, it was reported that before treatment, there is no detection, but after treatment, there was a detected gene. Even Spain, there was like, okay, 10 to the power 5, but 10 to the power 4. So a log reduction has happened, but it is not that it has been completely removed. So the challenge or experience number 2 that has happened to me very initially, I mean, along the first paper, I wrote this second paper where I just, that treatment plant was typically set with the primary treatment, USB reactor, aeration tank, and clarifiers. So I took the sample, I don't know why, but at that time I just took that, okay, let's take the sample. And in the first paper, we just, of course, compared this one, but when we completed entire result, entire samples analysis, then we saw that there is a log reduction, but it is not that it is going to finish right away. Of course, some of the times I would not go into this polyethylene glycol method or filtration method, which has the more precision or which can give you a better result. But still, that time itself, there was the question was that this was the case of 100 mLD plant. It's bigger plant, and we saw that there is some stepwise reduction happens. So the decay gradual happens or suddenly happens? That was the second question. But then we keep on keep on monitoring for 5-6 months, and we kept just monitor the sample. And then what we have found is that we analyze data. Now see, this is a published work in environmental research last month. So in this case, the August to September. So 2-month data, 2-month weekly data is presented here. Initial challenge that I told is that N gene and S gene, and this is the ORF gene. And N gene is, you can see that in the same sample, on the same date, I mean the overall, if it is like N gene is saying something else, it is less than 500 copies, S gene is around 400. I mean the variation among the sample I am talking about, because 10 sample we were taking from the Ahmedabad city. And ORF gene has shown the different kind of variation. So again, among the variations, and it's not that only N gene will show less and S gene will show more. The second case that is here being highlighted, you can see that I mean the 2000, this is the 6000, it goes N gene, and spike genes range has decreased. So then this is like one question. Then most of the time that I am encountered with the reviewer referees question that how to calculate the gene copies, whether we have to take the average of this or only one gene will give the gene copies, and like what. Of course, we have given that we put that, okay, the first of all, if not 2 genes are present, we take it a negative sample. But otherwise, if the 3 years present, we want to take average rather than going with the 1. But I think there is some discrepancies among the monitored genes, and which gene CT value should be considered for gene copy calculations. So that is, I consider it as a challenge number 3. Then there is I already told you that when we have seen that whether the treatment will remove or not, this is a 10 mld. Previously, I shown 100 mld, but now it is a 10 mld STP, which is a conventional treatment plant. And we have seen that this is a gene copy, this is a CT value. CT value, if it is higher, it means the gene copies will be less. So this is just for some audience, and gene copies here you can see that not completely removed. And I am talking about all the samples that has been collected for that month or during those period. And of course, it seems like N genes has a little bit less removal than ORF gene is being, easily removed and something like that. But of course, there were some questions that whether treatment really removes it all, or the treatment size or the STP size is going to affect it. When we, depending on the treatment size, we also monitored root zone treatment plant, which was around in the campus and which is 2.36 mld size. And here we have seen that the removal was much more, in the outlet or in the after treatment, there were a lot of things. You can see that there is a ultraviolet or sand filter, those things were there. Ultraviolet disinfection was not working. Chlorination was not there. But of course, if there is a one kind of course, for our comparison, we only take inlet. But this outlet is also going to be a very interesting point what happens and what remains in the system and how it is being removed. So this is a part of what we have found, that maybe the smaller size of the treatment plant is showing more fluctuation, and also how we handle the treatment plant or how it is being managed is perhaps also going to have an impact. Coming to the challenges number 4, that different removal for different genes. We also saw that not only that, okay, there is a different degree of removal from the different size of the treatment plant, but it is also that ORF gene, you can see this is green. Green means, okay, the lower genetic gene copies, and if it is red, it is higher. So you can see that from the ORF gene, for the both bigger size or a smaller size treatment plants, ORF gene is the one which shows little bit more removal than other genes. And in fact, if you will look into the data more closely, we will find that N genes is a little bit more resistant than the S gene, but ORF gene is more sensitive, it seems. So then whether this is going to have any impact on the wastewater surveillance data or not, and those things. Of course, I am discussing this as a just sharing my experience with the many experts who knows much more than me. Then experience and challenges number 5. Experience numbers, this one has been highlighted by Professor Rose, also for Professor Anna, that the variant type, the UK variant, what we have recently seen that S gene or spike protein genes of UK variant is not picked by or detected by TechPath. So it means that I was measuring ORF gene, S gene, and N gene, and now the S gene is not being picked up. So if I don't know that in a community how many the COVID patients are suffering from UK variant, the coronavirus, right? So in that case, that is also a kind of may raise some speculation. This is ENC number 6, that does treatment remove it all? Of course, I already talked, but here interesting point is that how the wastewater characteristic will impact the sweep. Of course, sometimes I feel that the ligands, purgeons of the humic matter, or a typical environmental engineer will be able to appreciate it, that okay, the removal might be also being associated with those other characteristics of this one. We just put a principal component analysis of our 3-4 months data, and then we have found that before treatment, this S gene and these genes, the virus component had. Of course, I have not taken a lot of other variables, but at least the simple TDS, salinity, or EC, pH, ORP. And then we have found that there is the high loading in the second component, but less loading in the first component. And after treated water, it changed drastically, and then of course you know that it has the higher. So of course after that, the samples are being differentiated based on whether they are left with the genes or not. It has to be interpreted in several ways. But these are the sample which is now I am revising for Chemical Engineering Journal, is that the temporal variability is absorbed in the renewable efficacy of wastewater treatment plant. Not only we have seen the spike or the different variation in the inlet water, but we have seen the temporal variability in the treated water also. So that is, and I already told you that ORF gene and S gene appears to be more sensitive to treatment than N genes. Now, the many times, this is a Bangladesh study which came again recently. This is the first detection reported there, of course a little bit late, but in this case we had done along the I mean not treatment plant but a sewer system and downstream and upstream and like that, and there were many interesting results. Of course I have not much time to focus on that, but the point is that where we need to the sample to tell about the community, and in a system where there is no wastewater. There are many cities in India or many developing the countries where there is no wastewater treatment plant. In that case, how to tell that how much community is affected? Then there is a challenge number 8, which means this is the second last challenges. That when I was comparing the results and a spike and trying to know that whether we have some lag phase or not, we started with this diagram. With this diagram is that here you can see this is the variation of among, so this is the variation among S genes, or this would, and this is confirmed cases, active cases, deceased person. So what to recover, what to compare with? Because if there is a lag phase, then the spike in the water will be maybe coming from the somebody which is not confirmed, and like that. So what to compare to understand? Of course, I came up with this solution, which is now again now it is available on in the public domain. That I took the percentage change that I have seen in my sample in the previous week, and also the percentage change that is being reported in the active cases. And then we have found this diagram, and we have seen that around 1 to 2 weeks of 2 weeks of the early warning is possible. But when we have now we have experience of, like, you know, that 6 month data is already available. Just somehow sometimes it is missed. But the point is that the CT values is coming exactly the same as we started with. So what is the spectrum change over the years? What is the, whether we need to be consistent among the compare, CT values observed in Japan and the USA and I mean India, how comparable they are? Whether that CT values is the same number of gene copies that is going to be equivalent to, or what? That is, I think, a thing that we can debate on. Now I would like to just summarize it. That these challenges that I have seen, but of course we have to think about, or I am being countered with that, how important your sweep is, or wastewater surveillance is, early warning, how much, and there is a, of course, 6 to 8 days, 10 days, 2 weeks, there is a, of course we need to, dealing with the variant, how the other, the tech path, we need to, I mean the kit can change, coefficient of comparison, whether we need to compare them with what. And then the effectiveness of the treatment, because it is related to the, like, okay, the several aspects, but of course, one is that decay, dilution, or accumulation. Whether in a system, gene that is related, because anyway, we are talking about, if not living the RNA, that means non-living RNA is likely to be there, because it is a kind of nanoparticle size. It is a kind of a colloidal particles. It will stay there and can it give a false signal? So it means whether there is a happening decay or dilution or accumulation, that is one. A spectrum of variation, I already just talked, that from where we started, now where we are in terms of the CT values. And whether infectivity can be rooted out or can be neglected, because we are detecting the not intact RNA. In fact, we break them in order to isolate them. The number of the people infected or trained or screening, what we can do. And the last but not the least, what if COVID gone? I mean, after the vaccination and like that. But what I would say, my summary of this slide says that whether it is a South Asian perspective or universal challenge. I think with this, I would like to stop my presentation.
All right, thank you, Professor Kumar, for the interesting summary of the 9 challenges. All right, we have a question for you. First, how the vaccination drive in India is going to affect the results in India, and why is it difficult to have a national level surveillance in developing countries like India?
Yeah, so this has a 2-part. One is that, okay, the vaccination drive. Actually, I am thinking that the effectiveness of vaccination can be estimated through the wastewater surveillance. In fact, I am thinking that if, let's suppose that in a parliament or in a place where everybody is vaccinated, can we find anything that is in their wastewater? If we keep monitoring those sewage points, can we see any signal there? And that way we can know that whether the vaccine is fully effective or not, or how it is going. So yes, I think the vaccination drive is the must, or I want it to affect our results, and sample becomes more and more negative. And the second thing about the national level surveillance, yes, I think among the experts, because when I am seeking a funding, perhaps I advocate it, and there are many points which can go against it. So that is why somehow some countries, even if with the little bit, okay, there are discussion points, but they went ahead with the surveillance. But in India, still we are not able to put it on the national level or even on the province level. So yeah, that is unfortunate.
Yeah, so to follow up the first question, you're saying about the once your vaccination increase, so the challenge here will be, of course, there's still no scientific confirmation is that when even for people who are vaccinated, they may still be carrier, So how will that impact on the stool sample? Will the virus still be shed, So I think just now Professor John Rose mentioned about monitoring to see the trend after vaccination will be pretty interesting.
Yeah. I mean, of course, the tricky part, thank you very much for explaining it together with me. That, yes, you are right that it can be still the carrier will be there, and but it will be interesting to see that how it responds our wastewater surveillance in a given community where everybody is vaccinated.
Right. Okay, there's one question for you. Another one. Do you think in diverse sanitation coverage like India and Bangladesh, where you've got rural area where there's no sanitation sewer system, if we collect real-time stool samples from the infected patient, will we be able to establish a causal pathway? I mean, i.e. rate of the virus shedding, the decay time, or wastewater viral load in the defined catchment area?
So I think this is a very interesting and a good research question, I would say. Because little bit it will be a bit difficult that, okay, the real time or the fresh, there are many studies which says that even if we will take after 8 hours, 90% decay can occur. There is a lot of the time thing is there. There is also whether composite sample or grab sample or those aspects are there. But still, I think there is a possibility that if we will keep monitoring, like I told or showed in my graph, that when I was comparing with my results and trying to get some meaningful outcome, I end up with the matching the percentage change. Perhaps in this case also, if we monitor and makes all other conditions constant, there will be a meaningful results can be drawn that can be helpful for prediction in a given catchment area.
Sure. All right, one final question regarding the effectiveness of water treatment plant process. Do the effectiveness solution exist, such as disinfection, RO membrane, chemical solution, etc.? And finally, the solutions is it going to be a combination of different solutions? What is your opinion?
Yeah, I mean, see, personally, what is happening is that I also believe that as a virus, it doesn't remain in the system because, of course, this enveloped virus and those things. But if we are talking about fragments, which is almost dead, and I mean this is and the results that is showing, we have found that there is no. We are monitoring even river, and we found that the among 90 days of the monitoring period, there were 3-4 days when there was a positive signals. So there are a lot of questions lies there. I do not say that chlorination is not effective or disinfection is not effective. This is definitely should or must be effective, but what is happening, I already told that even treatment plants, how it is being managed. Sometimes UV disinfection is not working, chlorine dosing is not enough, and those things. But of course, I'm not talking about viability. I am talking about just a detection of the fragments, genetic material. And that was found positive. And we have seen that temporal variation also. If there was a high load in the in influent, it reflected somehow in the effluent also after some time. Not even exactly on the same day, but after some time. So there are a lot of interesting questions. And solution, I don't know that what Ramone is talking about, that solution of COVID-19 or solution of having negative samples more and more. But of course, I think the more negative sample will be coming because of course, if there is a good treatment plant and if we are managing on this treatment. But unless until in India also we are saying that in one hand people are getting vaccinated, in another hand there is a people are being reported for positive COVID-19. So it will be interesting to say, but of course everybody, all of us are waiting for the solution.
Okay, thank you, Professor Kumar. Thanks for sharing the challenges. Yeah. Okay, we shall move on to the next talk. I need to share the screen. Just give me a second. Okay, the next talk is by myself and my colleague, Professor Karina Jin. Just a quick introduction of myself. I'm the director for NERI and also the director for Central NUS Corporate Lab. I'm a provost chair professor in the Department of Civil Environmental Engineering in NUS. All right, and as for my colleague, Professor Karina Jin, she received a Bachelor Engineering from Melbourne University, Master Engineering from NUS, and doctoral degree from MIT, which is a joint degree also with the Woods Hole Oceanographic Institution. Her research specialization is in water quality and ecosystem processes. We focus on understanding the fate and transport of emerging microbial and chemical contaminants of concern, antimicrobial resistant and algae blooms. All right, let me just hold on a second. Let me share the slide, share my slide. See whether it works. Can you see my screen? Does it? Can you see my screen clearly?
No.
No. Oh. Let me hold on. Just give me a second. Okay, got it. Does it work now? Okay, great.
Yes.
Okay, so in this talk, basically we're going to share some practical experience as we carry out surveillance for NUS hostels and residential colleges. We will touch on issues from sampling, design, laboratory analysis, and the challenges. So in this talk, there are two parts to it. In fact, this effort is done by myself and also my colleague, Professor Karina Jin. Now, first of all is that how do we come about doing this surveillance? Of course, the MOE, the Ministry of Education, is very concerned about university housing, hostel being a hotbed of high rate of transmission, especially with what just now Li Chin has shared with us, is that there is a high number of cases in the early days in the worker dormitory. So with that in mind, the NUS Provost and President is also very concerned. And in campus, as we all know, is that there are residential communal living. All right, so for NUS, we basically, there are 7 halls and 8 residents spread out around the campus. And there's a high density housing units in the university town. And all in all, there are over 10,000 students living in all these university housing. That is about 1/4 of the total student population. And if we look at the all this housing itself, there are some very old hostels, some high-rise building, and it's a very hilly terrain. Now, the objectives of this survey is basically, later you will see that in Singapore, excluding the migrant workers, in fact, the prevalence in the Singapore community is considered rather low, which is about 0.04%. Okay, so the President and Provost of NUS is very concerned that can we have a very effective tools to do early surveillance detection so that we can isolate student blocks at block level of residents accommodation, and then you do a more invasive kind of laser swab so that you can identify the students. So that is primarily the objective of why we do campus-wide wastewater surveillance. Now, so to do this exercise, of course, there are quite a number of considerations. First is, where are we going to sample and when are we going to sample? Then the next question is, how quick can the sample be transported to the laboratory for analysis? I mean, the laboratory run by Prof. Karina's gym to run the PCR testing. And the next very important issue is who are going to provide the resources. So NUS has committed huge funding to start off with this exercise. And at the same time, we also receive funding from National Environment Agency. So in fact, this exercise, like the slide shown, the second slide shown by Professor Li Chin, in fact, we work very closely with NEA on the whole monitoring protocol. So the approach is that we will sample all hostels and residents. And first of all is that how are we going to composite the samples, right? What is the most effective way? Of course, if you look at a normal wastewater discharge, you find that there's always a 2 peak period, right? First, as people go to do their big business in the early morning, right? And that's what we suspect initially, all right? And as we know, the whole testing cycle will need about 6 to 8 hours, all right? So if we do a daily collection of sample, in order to get the result out by end of the day, means around 8-9 p.m. in the evening, the sample has to be transported into the lab before 12 p.m. of the day so that they can start processing the samples. So, all right, and then what do we do when there's a positive case, right? So these are issues that we collaborate, we discuss closely with the Ministry of Education and the Health, Ministry of Health, to have the whole plan laid out before we carry out this exercise. So we started planning this wastewater surveillance in August last year. And to do this exercise, actually we formed a NUS planning committee, and I chaired the committee, and it involved people from various parts of the university, including the professors from civil environmental engineering. And then we also look at how can we optimize the transport route such that we can bring the sample back into the laboratory as quick as possible. That's why we get a professor from the department who are expert in transportation. That is Professor Raymond Ong. And then in order to do coordination, we get people from student affairs, where they're in charge of housing, Office of Housing Services, the campus infrastructure management, and then very important. The department is the Office of Safety, Health and Environment. So with all these people, and then we also have a statistician, Professor Yao Jiming, to look at how can we use statistical method to do the planning. So we look at the whole campus hostel drawings and to identify what is the best way. All right. So if you look at hostel, we find that I would say pretty much similar to every building in worldwide. You have toilet in the stack, and right at the basement or right at the bottom level, there's an inspection chambers. And then from inspection chambers, you join to a final discharge before you join to the main sewer line. So this, like all these round circle for the each building inspection chamber. And we have a final discharge here, right on the top left corner. So in fact, we study the sewer system for all the individual residents and come up with a plan for every one of them. So next is to look at statistical approach. So I mentioned earlier, like in Singapore, the prevalence rate estimated was 0.04% among the community, excluding the worker dormitory. And if we assume somewhere between 0.04 to 0.02%, so how do we, based on this statistic, how many minimum people should we sample so that what is the likelihood to get a positive sample, right? So that can base on statistic to determine. So basically, if we look at residential block itself is already a group testing in action, all right? And if it's a negative test, we clear the whole block of students. If a positive test, then you require individual testing using like nasal swab testing or saliva testing. So if we assume a prevalence of 0.2%, target relative effort of 25%, each sample should have a group size of 138%, means a sample should contributed by 138 people. Right? And then that shows if your prevalence lower, that will be the minimum ideal number of sample size of students. All right. So you can see that it ranged from 1,000 over up to 138. So if we assume 0.2% of prevalence and 25% of relative effective effort, then we are looking at size 138. So the other issue I mentioned earlier on is that how do we optimize to look at the toilet usage. So before we actually implement this, we did a campus-wide voluntary survey for students to submit their toilet usage pattern based on each residential hall. So what we found is that 71% actually clear their bowel daily in the hostels, all right? So that means is that if we can capture all these bowel discharge effectively, we can have a very high detection sensitivity, right? And then next is that, how about the toilet usage patterns, right? So we did the survey, especially clear bowel between different time, like before 5 a.m., 5 to 7, 7 to 9, every 2 hours interval. So what we found out is that there is, in fact, we were pretty surprised, 5 a.m. all the way to after 11 p.m. People are still doing, using the toilet for big business, So we did see a very, two higher peak, okay, 40% of hostelite in the morning between 9 to 11 and 1 to 3 p.m. All right, so the conclusion is that there is no very obvious to pick because initially we thought students go to lessons, right? They won't stay in the hostel, but you know that the student, their classes are at different time of the day. Sometimes they just stay in the hostel, right? And then, so the decision is that we need to sample 24 hours. And what we will do 6 hours composite samples. So every auto sampler will collect 4 composite samples, each lasts for 6 hours. All right, so in order to do this, we will sample at each inspection chamber of each block and plus the final discharge manifold. So in terms of collection frequencies, weekdays, during from Sunday noon time to Friday noon for most of the residence hall, except those with high population of foreign students, then we do daily sampling, including the weekends. So all in all, we have 111 auto samplers throughout the campus, all right? and 24 final discharge manhole. So if you look at it, we can collect up to 444 samples every day in the weekday, and we will only do the 24 final discharge. So 24 times 4 will be the number of samples need to be analyzed daily. So the approach is that we will test this final discharge. If there's a positive sample, then you will retrieve those upstream relevant IC sample to do the second round of testing. So what does that mean is that when the sample go to the lab by 12 p.m., by evening 8-9 p.m., you will have the first set of testing result. If there's a positive sample, then we will go to do a second round of the upstream IC sample. So by next day morning, we will be able to identify which block has a positive case. And then we can trigger, once we have detect a positive case, we'll trigger the NUS City and Health Environment Department. And then they will trigger MOE, NEA, sorry, this is not NES, NEA, leaching office. So this is a picture of all the auto sampler, and in order to have a better way of assessing the manhole, we actually make a special cover where there's an opening so that the contractor workers who pick up the sample can throw back the wastewater back into the manhole. And then the other issue here is that how can we capture every sample? So this is the idea that initially we implemented. So we actually put some kind of a sandbag system so that we create a tiny little dam, all right, so that we can capture water. And the frequency is like we try to do sampling every 2 minutes for 15 ml. So with the intention that we try to capture every discharge. So and in order to collect such a low volume, we need a vacuum pump auto sampler so that we don't because one experience is that with a peristaltic pump, if we run at such high frequency and so low volume, the auto sampler may over collect and spill the container of 4 liters each. So that is the reason we went for a vacuum pump. But the issue of vacuum pump is that it can only be effective for up to 7 meters. If manhole more than 7 meters, we have a problem of getting the sample up. All right. Now what happened is that after that, we found that there are challenges. All right. We find unwanted, unintended material in the sewer. People throw, even found a T-shirt, causing choking and backflow of wastewater. And then they are choking a sampling tube, high pressure in sampling hose, dislodge of volume control tube, overflow of wastewater, backflow of wastewater. So in the end, we also found that one of the type of auto sampler, because of the low water sampling and the high frequency, we have melting of component in the auto sampler pumps or kind of a diaphragm or this thing. So in the end, the decision is not to use a dam, and then we decrease the sampling frequency. So that is a good lesson learned. So all in all, we found that wastewater surveillance is an excellent approach to monitor response to COVID-19. Group testing reduces the need for large-scale invasive swab tests, especially in Singapore where the cases right now is negative in the community. There's 0 cases in the community. And the acceptable sample population size of from 130 to 714 sample can be pulled to reduce number to test for testing, and discharge behavior show the need for high frequency 24-hour composite sample. And the toilet habit of user is crucial for proper implementation. All right, with this, thank you very much. And now I'll pass the time to my colleague, Professor Karina. Stop sharing. Karina, you can share your screen now.
Okay. Okay, can everyone see my screen?
Yeah.
Hang on. Okay, so good day, everyone. So I'm going to continue with part 2 of the NUS sewage surveillance project. Just like to also acknowledge all the hardworking members on my team and very dedicated researchers, and also our collaborators, Dr. Ng Li Ching and Dr. Judith Wong from NEA, who really helped us tremendously to kickstart this project from their previous experience with their worker dormitories. So as Yong was saying, right, this project, basically our objective was to try and get that PCR result as quickly as possible so that management can follow up. And so for us, the goal was to ensure that we could get a PCR result. If it was positive, we could confirm and then report it within 24 hours. Okay, so that was the overall goal. So for us, we had to set up from a BSL-2 lab, we had to upgrade to the BSL-2 plus so that we could carry out this surveillance. And so that basically required us to put all the OSHI requirements and IBC requirements in place. And to go for the biosafety level 2+, we had to ensure that personnel were properly trained and that they worked in a buddy system. They had to go through an immunization vaccination program. And actually right now they've all gone through the COVID vaccination as well. We used proper PPE, including the N95 masks, which had to be fitted, as well as the disposable gowns and gloves, goggles, etc. And as with our BSL-2, we had to restrict access to the lab, making sure only authorized personnel could go in, and we had to keep all our samples under lock and key. So all the samples that came in and out were properly documented. The lab itself had negative pressure air system. We had 2 class 2 biosafety cabinets to carry out our analysis. We also had 2 centrifuges, which were capped so that it was aerosol tight. And because we anticipated many, many samples, we decided to go for an automated RNA extraction system. And so on top of that, we would have the usual, clean hood, QPCRs, and fridges and deep freezers. We also had to ensure that the wastes were properly handled. And so, any wastewater had to be eventually disposed of after it had been properly disinfected. So we use Faecal at 2% and let it soak for about at least 30 minutes and also autoclaved other consumable wastes. So we had a very stringent cleaning procedure put in place, making sure that our workstations were thoroughly cleaned every day using 10% bleach followed by 80% ethanol. So that was just to set up the BSL-2+, and by the time we got all the risk assessments done and all the SOPs done, we were very excited to get going. But as I'll explain later, we also hit a few challenges along the way. But anyway, before I talk about our challenges, maybe I'll just describe briefly our methodology. So it's basically a 4-step process, right? So we start off with sample preparation, followed by virus enrichment and concentration. Then there's the RNA extraction step, and finally followed by the RNA detection, which of course is RT-qPCR for the SARS coronavirus. So our workflow can be summarized as follows, right? With samples, when they first come in, we will make sure we wipe them down, spray them with 80% ethanol before we handle. And all our wastewater samples were actually heat inactivated prior to any analysis, right? So we would heat at 60 degrees for 1 hour. And then after that, we would clarify the samples by centrifuging for about 30 minutes at 4,000 G. And then we would go for the viral concentration, again, using centrifugation, and this time using Amicon filters to concentrate the virus. So this is at 4,000 G for 20 minutes. And then from there, we get about 150 to 200 microliters retentate, which we then use for extraction. So we purchased the Kingfisher automated extractor to help us in this, speed up the process, but it still takes about 40 minutes to load up the sampler, and the actual runtime is around 20 or 25 minutes. And after extraction, then we of course go for our RT-qPCR. So as Li-Cheng explained earlier, we followed the NEA protocol, which was to use the ORF1AB gene targets. And assuming if we got any positive hits, we would then use the N1 gene for confirmation. And for the process control, we use PMMOV, right, the peptide mottle virus. And as explained earlier, this is one of the viruses that are frequently detected in sewage. And so it's a good process control virus. So our first results, typically we would get within 6 hours or sometimes longer, depending on how many samples we have, but on average around 6 to 8 hours. And if, assuming we get a positive hit, we would then go to the next phase. And remember that when Yong explained that actually the first batch of samples we look at are actually the final discharges. So if we get a positive for the final discharge, we would then go upstream to look at where it originated from. So then we would go for the inspection chambers, which would be, it would be coming from a particular block. So from there, we could identify the block. We would confirm within about 12 hours, so that within 24 hours, we could report a result to our management, and then they could do the follow-up, such as swab tests, etc. So that's the game plan. And then maybe just a little bit more detail. So if we look at how we analyze the samples, in a way, we take in about, if we had all auto samplers working, we would take in about 400 sample bottles, which is a lot to analyze. So that's why we cut down and just look at the final discharge samples. But on top of that, each location would have 4 time periods. To cut down the number of samples for analysis even further, we pooled the samples for the sort of non-peak periods, and that would be the night sample. So eventually we pull together like time periods 2 and 3 here, which are the night samples. And then we end up for each location having 3 samples to analyze for the final discharge. But in practice, what we found, especially during this period where there are not as many students perhaps living in the dorms, sometimes we don't get any sample from the manholes, and sometimes the final discharge itself has no water, but we found sample in the upstream inspection chambers. So in that case, then what we did was we pooled equal volumes from the inspection chamber for each time period, and then used that the pooled sample to test for the coronavirus. In terms of the RT-qPCR method, our 2 targets include the SARS coronavirus 2 and the PMMOV virus, which is the process control. So we followed the primers probe sequences as shown in this table here, and the reactions, the reagent conditions are shown here. So as we ran our sewage samples, we also had positive controls. So we used the twist synthetic RNA control for the SARS virus, and we use the G-block PMMOV for the internal process control for PMMOV. So we actually had 2 QPCR machines, and we ran them in parallel. So one was for the PMMOV and one was for the SARS virus. So in terms of the number of samples we handle on a weekly basis, so far it's been averaging around 550 samples. Sometimes we have a little bit more, sometimes a little bit less, because the students are not always in the dorms. Sometimes they go home for a period of time. Of these 500 or so sample bottles collected, because of the pooling process, we actually end up looking at about 350, 380 sample bottles per week. And of these, we do the QPCR tests. There's a smaller subset, around 250 tests per week. So that's the order of testing that we've been doing so far for our dorms. And in total, I guess, the measurements to date, we've collected about 7,000 samples since around mid-December. We've actually tested about 2,400 samples, but so far we have been, well, we haven't had any positive detects. So I guess that's good, but in some ways it's kind of not as exciting as some of the other data that you've been presenting earlier. So hopefully, though, we will keep it as no detects. But we did face a number of challenges from the beginning as we set up, and I think this is a good time to share with those who are just about to set up a sewage surveillance on your campus or at your institution, and hopefully we can not repeat some of the things that we went through. So this is actually a summary of some of the issues faced by many other institutions. This is sort of compiled from the literature. All right, so we at NUS encountered in particular supply chain delays, right, especially in consumables and in equipment. We also had auto sampler breakdowns, and we still to this day also face challenges in ensuring that the auto samplers work on a daily basis. We've been trying to optimize the lab methods, and I would like to thank in particular NEA because they really helped us a lot with the protocols. And biosafety issues, especially contamination. In fact, this was one of the biggest issues that we had to tackle from the very beginning. So after setting up the lab, getting the BSL-2 plus in place, which took us a while, we were very excited when we've got our first batch of sewage samples. And at first it went well, but very quickly we realized that we started getting positive contamination of the SARS coronavirus. Actually, it was probably the yeah, well, anyway, so we got these false positives in the lab, which we had to troubleshoot and try to figure out where it was coming from. And eventually we found that it was coming from the QPCR machine. And with that, after identifying it, we did a deep clean of the lab, right? We wiped down everything with bleach, but that didn't really help. I mean, we even wiped the ceilings, we wiped the walls, everything we could see. But we were still getting the false positives. So eventually we had to go for full fumigation of the lab. We also changed all the consumables. We had to restock the reagents, so it was very expensive. And we zapped everything with UV before we used it. We also realized that we had problems because our QPCR machine was in the same area as where we were handling the samples. And unfortunately, this is one of the constraints that we had at the time, because we only had one room, BSL-2 room, which we upgraded to BSL-2 plus. And this may be a constraint that your institution maybe, or your lab may be facing as well. But if you can, you should try to keep the the non-PCR work separate from the PCR analysis. We also realized that we had to prepare the reagents, aliquot the reagents in a separate clean room to avoid cross-contamination. And again, we kind of learned this the hard way, because even after cleaning up the main lab, and even when we had taken the reagents out and prepared them separately, we didn't realize that actually we also had to change the people who did it, right? So we had to have separate teams we had to have a split team, separate team to handle the reagent preparation, and they had to be completely separate from those who are working in the main lab. Yeah, so now what we do is we periodically check for possible contamination sources, and this is quite easily done by leaving exposed open blank vials in strategic areas in the lab, and you leave it overnight, and then subsequently you can do your QPCR tests to see if there's any positives, and then you can identify contamination areas. So to show you what happened during this learning exercise, this is our setup for our lab. The entrance is here. Sorry, I'm not sure if you can see my mouse very clearly. So at the beginning, we had to do everything in the BSL2, which was here. And actually, there was a little adjacent room which had a concentrator as well as a BSC. So we thought we would do the PMMOV maybe in this room, the QPCR for that, the preparation, and then sample preparation, the main sample preparation here. So after we did the blank vial test, we realized that it was the QPCR that was giving us the problem, and it was the source of contamination. And when we left out the blank vials, we found that, you know, these areas were heavily contaminated, right? The area of the star showing the extent of contamination. So with that, we had to do the deep clean of the area, and we fumigated the whole lab. And now what we've done and what we've learned from this is that we should keep the preparation of the reagents, which is done in the clean hood in a separate area, completely separate from the sample preparation. We rehouse the BSC and the concentrator, put everything into the main lab, and then shifted the QPCR into a separate room, which could be, you know, sealed off from the rest of the main lab. So with this, we managed to overcome our contamination problem, and thankfully, well, touch wood, everything's been running smoothly since. So we have a PCR room, a non-PCR room, and a preparation room, and all these are kept separate. We also hit supply issues, especially recently. There's been a shortage of Amicon because everyone's using Amicon. So we're looking at alternative concentrators. One of these is the Pierce concentrator, and this is made from a different material from Amicon. It's made from PES, polyether sulfone. It also allows a little bit more volume in the tube. If you look at our preliminary results, basically the concentration factor is about the same, right? It's not significantly different, but there is more variability attached with the Pierce concentrator compared to the Amicon. And if you look at the CT value that for the sample, it's a little bit less sensitive. The CT value is a little bit higher, about 1 CT unit. So we're still doing some more tests to verify this because, again, the supply issues. We're also trying to order in the Pierce concentrator, but this is taking some time to come in. Of course, there's also the PEG precipitation, which we could do to replace the Amicon. And it works very well, equally well, especially for clean samples. Even for the inhibited samples, we found that it's a little bit more sensitive, but the main problem with PEG is the time. So it would add at least another 12 hours to our analysis, and time for us is a major factor. So hopefully we don't have to go to PEG, but it really depends on the supply issues, whether we can get Amicon or replacement for Amicon. The other big issue that we faced was PCR inhibition. And, you know, I think about 17% of our samples routinely gave inhibition. And so this is problematic because in order to overcome that, we had to dilute the samples by about 10 times. And this takes another 1.5 hours to our analysis. Also increases the reagent costs. And, you know, with more dilution, it also means the sensitivity may not be there for the detection. We are currently doing some tests to try to optimize this and to remove the inhibition problem, and it seems to be working. So so that at least is moving forward. So other challenges that we've had include staffing issues. Currently, we have a team of 8 people, 7 who are working in the lab, and 1 person who is running around taking care of the auto samplers. Actually, quite a lot of auto samplers. There's 111, that's how Yong mentioned. But for us, you know, it was a challenge to get this, the manpower operating in a way that was fair and also so that we could monitor 7 days a week, even during the public holidays, and make sure we could report any positive results within 24 hours. Right? So we work on a roster and on a shift basis, and that's why I'm very grateful that my researchers are working very hard and they're very dedicated. This is another minor challenge. It was a challenge, more of a challenge at the beginning, but since then we've managed to get more sampling bottles in, which means we don't have to wash as much. But we did have bottle washing woes at the beginning. We have now got sufficient bottles that we can color code on a daily basis, and so that helps to in the analysis. We tried to get a dishwasher in, but it took 3 months to come in, supply issues again, and we made up for it by getting student part-time help. This is an interesting picture because sometimes the wastewater that comes through is very strange, right? So this is real colored wastewater rather than color-coded sample bottles. So in future, I think what we will be exploring is the use of multiplex RT qPCR. With some of the other gene targets, we could supplement with our current ones, and so that's something we will continue to do. We also have a ddPCR in the lab, so we're also going to try and ramp up and maybe use the ddPCR. And as an aside, because we're collecting sewage and we are extracting DNA or RNA, we're also going to try to develop a multiplex viral system to look at other viral diseases, including dengue and maybe influenza, etc. And we are complementing that also with chemical analysis of disease markers, including antimicrobials and antibiotics. Okay, so with that, I'd like to also thank NEA, and who has been a great supporter of this project, and also NUS. So thank you very much for your attention.